Suppose at some point I can stop my video, right? So internet becomes, I don't know.
Sure. We don't need to see your pretty face. We all know you're good looking. So I don't know what's going on with YouTube. It says preparing to stream, but it's not streaming. Let me double check, make sure that all the settings are correct. Yep, we're streaming. Okay. Hello, everyone. Welcome to another Quantum Matter seminar. It's my pleasure today to give you Jose Hoyos from, I'm not sure I'm pronouncing it correctly with Portuguese accent. I'm using my Spanish accent.
Well, Hoyos is Spanish, so you are
Right.
perfect.
So, and he's going to share with us some work he started, I believe, while on sabbatical in Max Planck in Dresden. That's when you told me the first time about this, I think. And uh, I give you Jose, who's going to tell us about dynamical phase transitions.
Hey, thanks, Adrian, for this invitation, and you all for being here. If you have a question, just raise your hand or just go ahead and interrupt me. I prefer when there are lots of interactions. Um, and I'm going to try to make this very quick, so we can go directly to the point and get the main fees out of it. Okay, I started by thanking my collaborators, José Cândido Xavier and Rafael Costa from Universidade Federal de Uberlândia, which is a state nearby São Paulo state, where I am. And Minas Gerais state is supposed to have the best food in Brazil, but there are many controversies on that. Okay, um, so what I going So what I'm going to give you is an introductory review on dynamical quantum phase transitions and Griffiths effects in equilibrium quantum phase transitions. And then we are going to put these two concepts together, and I will give a definition, the existence, and the origin of what we've been calling dynamical Griffiths phase, and wrap up something with the conclusions. Okay, what's a dynamical quantum phase transition? So the thing we are interested here is closed dynamics, real-time dynamics of closed quantum many-body systems. This is a topic that has been growing recently, mainly because experimentalists they are now being able to really do experiments on closed quantum many-body systems. Of course, it's not entirely closed, but for a window of time, it can be considered as a closed system. And the interesting phenomenon on that is thermalization, lack of thermalization, and many others. So that's the context of what I'm going to tell you today. So a dynamical quantum phase transition, the best thing to understand it's like making a parallel to equilibrium phase transitions, where the free energy is a non-analytical function of temperature. And here, what defines a dynamical quantum phase transition is that some physical quantity can be a non-analytical function of time instead of temperature. So to give you an example, it's the Loschmidt amplitude. So we start with some initial state, evolve it unitarily according to some Hamiltonian, many-body Hamiltonian, and see if it comes back. So the Z of t is called Loschmidt amplitude, and the modulus of it is the return probability. So it has, since there is an exponential of something that's related to energy, this has the flavor of exponential of minus beta t. So I call Z, what people have been calling Z, is some sort of a dynamical partition function. So in analogy to the equilibrium partition function. And this Ft here would be some analogous of free energy, dynamical free energy. And we know from the equilibrium phase transitions by the work of Yang Li and Fisher that phase transition happens when the zeros of the partition function, they touch the real temperature axis. So if you have a zero in the partition function, the free energy, you take a log of zero is a non-analytic. So when these zeros touch the real temperature, you get a equilibrium phase transition. Now we do the same, but for this quantity here, which can be, there is a mathematical theorem that it can be expressed as like that. So mu is an entire function, meaning that's analytic, so there is no zero here. And there is the productory of the zeros. You take the log, so these zeros, which happen in the imaginary time complex plane, they will eventually touch the real-time axis, and if it happens in this way, we say that at that time instant, there is a dynamical quantum phase transition. I drew here one example that these zeros pierce the real-time axis at a single time instant, but there can be also that these zeros, they are grouped in an entire area, and this entire area intercept in a finite time window the real-time axis, and therefore we call it, well, there is non-analytic happening at the entry and the getting out of this time window. In the middle, although you would say, oh, there is many non-analyticities here, but in the middle, the system, thermodynamic limited, recovers analyticity. I will come back to this point later. Okay. So a little bit of equilibrium quantum phase transition. This is just for setting up the stage. So we are looking at the transverse field is in chain. So there is the interactions, which are parameterized by J. So this term wants the spins to be parallel. And sigma x encodes the quantum fluctuations. So sigma x on spin up or spin down flips the spin. So these two terms compete. When H is greater than J, the system is in the paramagnetic phase. So mostly they are pointing to the right. Right is the x direction. And when H is smaller than J, the system is basically in the paramagnetic state. There is a Z2 symmetry breaking between up and down. Up and down is the Z direction. And I drew here in blue the spectral gap. The system is gapless only at the critical point. And in dash red is the other parameter, which is finite. The ferromagnetic phase is zero in the paramagnetic phase. So a dynamical phase transition. So let's define the non-equilibrium protocol. So we start with initial state, supposedly the ground state of H naught. And then we quench the transverse field from H naught to H. And this is the Hamiltonian that will evolve the system. So I'm going to use the transverse field is in chain, which is somewhat simple because we can map into free fermions via the Jordan-Wegener transformation. and get, in the case of the clean system, get analytical solution if you are dealing with periodic boundary conditions. And that's what I'm going to do here, periodic boundary conditions. So let's not going into details, but these, after some pages of calculations, you can compute the return probability, the Low-Schmidt amplitude, or the dynamical partition function. You can compute it. It's a productory. What is what's here is k, which is the wave vector after you Fourier transform this the free fermionic Hamiltonian. So let's not pay attention to this productory here. I will plot it in the next slide. But what I want to tell you is that we can compute this analytically, and that's the solution. If we look at the zeros of this dynamical partition function or the Low-Schmidt amplitude, they have the real part, which is written here, and the imaginary part, which is written there. And what happens here is that this depends on omega, which is the dispersion relation, and depends on this epsilon k, which encodes the initial and the final Hamiltonian. So there is an H naught and J here. Okay, so let's see what's happening. So these are the Fisher zeros, the ones of this productory here, or those numbers here. The dashed lines are the thermodynamic limit, and the dots are for a finite size chain. I don't recall exactly the size, but maybe 4 times the number of dots here.
Sorry, quick question. Can you?
Sure, go ahead.
Just a clarification question. So in the last slide, your omega sub k is basically that's the dispersion of the chain in this Majorana basis. But what's epsilon sub k?
Yeah, epsilon. It's well, I just you can compute it, and omega k appears here, and epsilon k appears there. This epsilon k, I just want to separate, because omega k is the dispersion relation, which depends on only on the final Hamiltonian, omega k here, but this epsilon k depends on the initial and final Hamiltonian. So this epsilon k tells you how the initial state is in the final state. It's so you are projecting the initial state in the base of the base of the final Hamiltonian and let it evolve. So this epsilon k somehow it encodes this projection.
Okay, thanks.
I don't have a better idea for that, but that's what I found.
Okay.
But yeah, okay. So let's see what happened here. So here the final field is 1/3 of the J, meaning that the quantum phase transition was crossed. So I'm starting here. H is infinite. So that's what I'm going to do. See, I put H. What is this? Here. H naught is infinite. So I'm deep in the paramagnetic state initially, right here. And then I will quench to some point in the ferromagnetic phase. So when I quench H to 1/3 of the J across the transition, the equilibrium transition, and the dynamical the zeros of the dynamical partition function are those dots here. You have 3 branches here. These keep going. There are infinite branches. But this branch cuts the real-time axis around here, too. The third, the second one here, and so on. This interception of the real time, these are these cusps here that we are seeing. So you see this is around 2 and this is around 2, around 7, and same thing here, around 7, and so on. So these cuspids are the dynamical phase transitions, where the zeros cross the real-time axis. If I quench H to some value larger than J, the zeros are up in the sky. They do not cross the real-time axis, and the free energy, the dynamical free energy, is an analytic function. There is no cuspids, and this infinite derivative, and the infinite function, analytical function, analytic function. I put 2 examples here, 11/9 and 3J, and this is 0 and 1/3. So what's the message? The message so far, you could say, well, it seems that when you cross the equilibrium quantum phase transition, you do have a dynamical quantum phase transition, and that's somewhat exciting because you are using a concept of equilibrium to say something about a non-equilibrium situation. So the question that arose at the time was if there is a one-to-one correspondence between dynamical quantum phase transitions and equilibrium quantum phase transitions. For most systems that are short-range interaction, this seems to be true, but there has been lots of, now we know that there has been lots of examples where this is not the case. Especially with long-range interactions. Yes?
Hi, Jose Vlad here. I just want to ask you, you can talk about dynamics close to equilibrium, but you can also talk about dynamics far from equilibrium. So if you are very near equilibrium, this is really not non-equilibrium. It is just kind of in the sense of linear response theory being calculated from equilibrium theory. So,
yes.
The stuff that you're mentioning here, refers to infinitesimal departures from equilibrium or being far from equilibrium?
Oh, it's very far from equilibrium. See, I'm starting deep in the paramagnetic side of the phase transition. I'm starting practically here in the infinite sides. And then I quench to H.
Right.
And I cross the transition. H is 1/3 of the J. So I'm very, very far from equilibrium. Here I put H to 0. So from infinite to 0. So this is, there is no way this is near equilibrium.
Right, okay.
You excite the system a lot. There are lots of excitations. You need all the high-end states to evolve it. Yeah, so that's not something that you can tweak a little bit or use linear response theory.
Great, thank you.
So I was saying there are some examples, especially systems with long-range interactions, that people have seen that you do a quench that do not cross the equilibrium phase transition, but you do have dynamical phase transition, and also the other way around. There are other examples that you do cross the equilibrium phase transition, but does not have dynamical phase transitions. So meaning that there are lots of things going on and lots of things to be understood. But today we are keeping with the transverse field is in chain, which is very simple, and there is this correspondence. So I'm going to talk about disorder. People have been studying this system in the case of clean systems, but I'm not going to do that. I'm going to introduce quench disorder, meaning that your sample for some reason is not homogeneous. This coupling constant here is distributed according to some distribution and has a finite width. So let's start with the equilibrium case, the ground state of this system. Suppose that you have a transverse field that is larger than all the J's. So this is intuitive. If all the fields are stronger than all the couplings, you are in the paramagnetic phase because, well, simply energetics. Likewise, if all the fields are smaller than the J's, you are deep in the ferromagnetic phase. So you are in the Z2 broken phase, which I call conventional ferromagnetic phase. However, if you are in between, and that's what where is the exciting things happening. You can see that some of the couplings are stronger than the field, even though the fields are greater than the great majority. So in the great majority, the system is a paramagnet. The bulk is paramagnet. But because there is a chance that you can have what we call a rare region, meaning a region where all the couplings are locally stronger than the field. Suppose that you flip the coin and you got heads many times. And so this rare region is rare because it's exponentially rare. But locally, it is in the ferromagnetic side because all the couplings are greater than the fields, the transverse field. So it's just like you have a ferromagnetic island in a paramagnetic bulk. Of course, it cannot develop true magnetic order because this island is finite. So it has to fluctuate. It cannot be up every time. So it will slowly fluctuate between up and down, but mostly coherent. If you are at very low temperature, if you are at 0 temperature, it fluctuates coherently. It does not nucleate a domain wall. It's a coherent fluctuation between up and down. And this happens, time of these fluctuations is exponentially large in the size of this rare region. So this slow dynamics is related to a small gap, small energy scale. And this rare region is very easily to excite because the up and down states, they are nearly degenerate. So it's very easy to excite it. And for that reason, it kills the gap. So if you see what I'm plotting here in blue, this is the spectral gap. So whenever this field is inside the distribution of the J's, the spectral gap vanishes because of it's very easy to excite these rare regions. So the spectral gap is 0 in entire region surround the quantum critical point. And this entire region is called Griffiths phase. Although I give you a wave hand argument, this is a rigorous statement, which was shown by Griffiths. Okay, so that's the feeling of the Griffiths paramagnet. It's just another slide that if you wish to, for the aficionados on Griffiths phase, you can compute, for instance, the low energy density of states coming out of these rare regions. So you just look at the probability of finding a rare region, which is exponentially small. And each rare region contributes to the low energy of state with a state that is delta above 0. And delta is related to that, is the inverse of this long time tunneling rate here. So the rare region, although it's exponentially rare, and someone could say, who cares about exponentially rare things in your bulk? It has an exponentially small, it puts exponentially small energy state in your system. And if you compute the low energy density of state because of these rare regions. This exponential fights against this exponential, and you get a power law. And you can see that you get a dynamical exponent z here, and the z can goes to infinite if d nu is less than 2 in general. For the transverse field is in chain, nu is 1, d is 1, so d times 1 times 1 is less than 2, and that's the case. So z can go to infinite near the quantum critical point. So meaning that these rare regions are dominating entirely the low energy physics, mainly because it killed the gap, right? The bulk is gapped, so the bulk doesn't care about the any low energy excitation here. Okay, so that's what I
can just ask. The gap, you said the gap goes to 0 outside the Griffith. Is there a finite gap, rigorously speaking, outside the Griffiths region? Because my understanding was the Griffiths region is not sharply defined about it.
It is sharply defined if you have a sharp cutoff for the distribution of the J's.
Oh, okay. Now I get it. I thought for exponential distribution it wouldn't be sharply defined.
Okay, if it doesn't have any bound, then you don't have the classical paramagnet or the conventional paramagnet. You have always the Griffiths paramagnet.
Okay.
And yeah, but let's not talk about unbounded distribution.
Right.
Okay. All right. So now let's enter dynamics, right? I don't want to make it too long. So what will be the quench protocol? We start deep in the paramagnetic phase. H naught is infinite, so the initial state, everybody is pointing to the x direction. And you quench H naught to H, which is between two values, J weak and J strong. For simplicity, I will consider there are only two values for the coupling constant. It can be either weak or either strong. Okay. So if I do a quench that is between these two, I will make sure that I do a quench to the Griffiths paramagnet. I do not cross the quantum critical point. So in the clean case, if you do not cross the quantum critical point, remember that the dynamical free energy is analytic function. I will not cross the quantum critical point. I will go from the classical paramagnet, H naught infinite, to some point in the Griffiths paramagnet, where the only thing that happened was that the spectral gap vanished, but it is still a paramagnet. And see if something happened. And that's the result of simulation for systems of size 50, 100, and 150. So if you start with 50, which is blue, you get some sort of peaks here. It seems there are some non-analyticity happening in time. If I keep increase it, now I put 50 more sites on the same chain that I had before. Some of the peaks seems to have vanished or something else happened. For instance, this peak here, there is no peak anymore. And if I keep increasing, peaks come back. And well, it's kind of a mess, right? So my job here or my task in this seminar is to make sense of this mess. And I promise you, it's very easy to understand all of this. But we have to go slowly. So let's go to understand this mess. But before that, let's just see what we have at hand. I just told you about the quantum Griffiths singularities in equilibrium, which is related to low energy, long time physics, right? So mostly when you look at the effects of quench disorder in phase transitions, you ask what disorder does, and the disorder does things not at short time physics, but only at long time physics. But look what's happening here. This is short time physics. This is scale of 1 or 2 in T. So this is, in this situation, whatever I'm going to tell you, this is short time physics. Nonetheless, it's related to those rare regions that I told you. So those rare regions in this non-equilibrium situation, they are fast. And I'll tell you why they are fast. Okay. So how do we deal with this problem? So I do the following strategy. I analyze a single defect. And I will tell you that yes, a single defect matters. So what's a single defect? I have 2 couplings. One for the rare region, which is strong. Remember, the rare region wants to be in the ferromagnetic side. And outside this rare region, the couplings JB, B of bulk. So I have a chain, I don't know, 100, 200 sites, and I have a rare region of 5, 6, 7 sites where JR is stronger than JB, and I will quench H from infinite to H, which is in between. Okay. So let's start. I will start with a rare region, which is not rare. It's just a single pair, size 1. And just to start, JR is the same thing as JB. And the field is much stronger, 10 times this coupling. So as we know, there is no, this is the clean case. And in the clean case, all the Fisher zeros are up in the sky. They are not crossing the real time. But now, let's make JR 2 times what we had before. Now the Fisher zeros, they change a little bit. And I keep increasing 3 times, 4, 5, 6, and so on. So that's my animation. So I make a strong rare region here, which is 3 times bigger than H, and I don't see any crossing of the real time. Of course, because this is not a rare region, right? This is just a single pair. So the rare region, I told you, it has to be lengthy. So let's increase its size, 2. Now when I have 2, I saw that 2 zeros migrate down here. I have 3. Oh, now 3 zeros migrate here. And since that one cross the real time axis. And 4, 5, 15. Okay. So 15, I have zeros that migrate here. I have 2 sets of zeros, 1 set up there and another set up here. And since that a new singularity developed in the dynamical free energy. And see the size of this singularity. The blue one is the clean case, and I multiply the clean case by 10, so you could see it. Okay. Conclusion so far. Rare region.
Quick question.
Yeah.
What is the size of the chain you are simulating in as compared to the size of the rare region?
Yeah. This is here. Since it's frame, I don't remember, but I thought I put 200, something like that.
Okay, so you don't think that there are any finite size effects in these?
No, here is not. Yeah. Okay. Don't worry about that. So the conclusion so far: a single rare region induces Fisher zeros arbitrarily close to the real time axis. So those zeros here. And it splits the zeros into 2 sets. And so it's an obvious observation. I like it because I have an interpretation for these 2 sets of zeros. I will do the following interpretation. I have a bulk that is dynamically decoupled from the rare region. I mean, I have two open chains undergoing their own quenches. There is a little caveat for this, but I will come back to that. But if I do this interpretation, what's the conclusion? Well, a rare region, I have the rare region here, right? And I do the quench that cross the rare region quantum critical point. Also, the rare region is finite. You cannot say about quantum critical, but in the parameter space, the rare region the quench crossed the rare region quantum critical point, but did not cross the bulk quantum critical point. So if you do a quench that do not cross the phase transition, as Vlad was inquiring before, you barely excite anything because you go from a paramagnet to a paramagnet. You just create small excitations and you can use linear response or whatever you like it. So the bulk is barely excited and remain in the same phase. But the rare region now is fully excited because you cross its phase transition, its quantum phase transition, meaning that the eigenstates, which are excitations out of the ferromagnetic phase, is very different in character from the paramagnetic state. So there, you expect the region to be highly excited. So what I did here was the following. I started with the zeros, these dashed lines, the clean case, and I keep increasing the coupling of the rare regions, and that's the path that these Fisher zeros those are the paths of the Fisher zero in the imaginary time, imaginary in the complex plane, imaginary time complex plane. So some of the zeros came here, some of the other zeros of the second branch came here, some of the zeros came from another branch that's not there, but they start putting zeros here in these, which cross these, the real-time axis. And if I do the following, I will get a rare region, a chain, an open chain that has the same quantum quench protocol. The zeros of this open chain are the crosses here. So they are on top of what we had before. So that's why I told you that I have the dynamics of this rare region decoupled from the bulk. Because the zeros of this open piece of chain is on top of the zeros of the entire system, those set of zeros that goes up here, right? They are not they have nothing to do with the sets of zeros that up there in the sky. But if I get the bulk, and I do the same crossing, open bulk, I get these pluses here, which do not match the zeros up there in the sky. But I don't care because these zeros up here, they give just analytical contribution to the free energy. The non-analytical contribution are all coming here. So the non-analytical contribution are coming from the rare region, which is dynamically decoupled from the bulk. But the bulk is not dynamically decoupled from the rare region. So that's something that is kind of weird, but that's the result of the calculation numerics. So by the way, I'm doing exactly the diagonalization here. There is no approximation and nothing like that. Okay, it's free fermions. We can do large spin chains, 200 and 300 easily. Okay, so what happens if I put two defects? So I have one defect here and another defect there. do these ray regions talk to each other? And well, this slide over busy, but I will go slowly with you guys. So what's in orange? That's the dynamical free energy in orange here. And you have some orange dots that are up there and some orange dots that are down here. So what's the orange? Only one ray region, meaning that the second ray region, I put its coupling equal to the bulk, exactly equal to the bulk. So I have only ray region, and we have what we had before. One set of zeros here and another set of zeros there. So the green, I have another ray region. I have this ray region, but this first ray region I make equal to the bulk. So again, we have what we had before. One set of zeros down there, another set of zeros up there, and I have this green line here. Now I will have both ray regions. That is the black. When I have both ray regions, one here, another there, I have these sets of zeros black here and two sets of zeros black there, and they do match. And I don't know if you can see, but the black is below the dashed red. The dashed red is the sum of the green plus the orange. If I get the green and sum the orange, I get the red dashed red, which is on top of the black. So meaning that these two ray regions are not talking to each other, even if I'm doing dynamics. So there's a more example. There's another example. I did many examples of that.
Wait. Does it depend? I mean, they are a finite size, and also there are a certain distance between them. So presumably, if they are very close to each other, that's no longer be true, right?
Yes, that's true. And I checked that. If they are close to each other, closer than the bulk correlation length, they will talk.
Okay.
But since they are rare, they are very diluted, so they are, in principle, far apart in real system, right? They would be far apart, farther than the correlation length of the bulk, because the bulk is paramagnet. Remember, so it has a short correlation length.
Right, makes sense. Thank you.
And in my simulations, I put one ray region in the bottom and another ray region on the top of the ring. So they cannot be, at least in this simulation. Of course, I did what I told you, put them close, and they start to talk with each other. But they take a while to talk. They do not talk right away. It takes some time to talk, and I will come back to that point later. So that's another example of what I'm doing, and I put one ray region, another ray region, and everything is matched. All the non-analyticity that we can understand come from these ray regions that are practically isolated. So we can make now understanding of that mass that I was telling you here. So each peak here is due to a ray region. So there is this ray region, and it probably comes up again here, and so on. So this is another ray region, which will probably come up here again, and so on. So if you have access to the microscopic of your system, you know where are each ray region, and you know exactly what their couplings are, and you can do this quench of many finite size ray regions and see what they are doing. And that's what I did here, right? When I sum up the green plus the orange, and if I have more ray regions, I would have other peaks, and you just sum them all, and that's it. So that's the conclusions that I find it very, very neat. So just to see what's exactly going on there, I will do the following. I will do the what's this quantity here? this quantity, I'm computing the evolve time of the local Hamiltonian. What's the local Hamiltonian? Is the local fields term plus the coupling to the left plus the coupling to the right, half of it. So the entire Hamiltonian is the sum of these EI operators. And I'm computing the expectation value of EI in time. So I'm not doing that return probability anymore, or the free energy, dynamical free energy anymore. I'm computing locally the energy density above the ground state. So I'm removing the ground state of it. So I had the minimum 0. And this chain is the following. It has 60 sites, 0 to 60. We can go further. I just put 60 so you can better visualize. Otherwise, I would have 300 here, and it wouldn't be so visually not be visually nice, understandable. So the bulk is 0.2 H. So the bulk is deep in the paramagnetic side. And one rare region is site 20, which is this one here. And another rare region is site 5, which is this 2 from 40 to 45. And they are deep in the ferromagnetic phase, their own ferromagnetic phase. So you do the quench. And the blue, meaning that there is no excitation at all, because this thing is 0, near 0. So you see that the bulk is mainly blue. So there is no excitations in the bulk practically. But there are lots of excitations in the rare region. So you can see even the light cones here of the quasi-particles propagating ballistically. But they do not tunnel to the bulk right away. So they remain confined. So the rare region is excited and the bulk is cool. So what's in B here, in the panel B? Panel B is the current, is the energy current. So this is the continuity equation, and I can get this guy here from Schrödinger equation. And the continuity equation in discrete time is just that. And to solve this equation here, I know how to compute this commutator. This J has to be this. So it involves sigma Z and sigma Y. So this is the energy current. And I compute the energy current. And you see the energy current is all confined in the rare region as well. So green is 0. So there is no energy current to the bulk. So all the energy current are confined in the rare regions. So again, rare region is exciting, bulk is cool. And okay, now we can wrap up many rare regions together. Each rare region will have its own, let's say, its own time instant where the free energy is non-analytic, its own dynamical quantum phase transition. So one rare region here, another there. And then in the thermodynamic, you'll have many rare regions. And if you are talking about bounded distributions, they will probably be more or less alike. So you have many of these zeros due to each rare region. And they will cluster it then into an area, not in just a single line, but in an area in the complex plane, in the time, the complex time plane. And this region between these two time instants is what I call dynamical Griffiths phase. So if you have a finite system that you can simulate in laboratory, you have many peaks here in this time window. as I told you, if you are going to the thermodynamic limit, then there is a huge number of zeros here, so they become dense, and this entire region here become analytic. And the non-lattices will appear only on the left and on the right. And this is some simulations that I did here for this case, but I will not bother with the details, too much technical. So the conclusions is that Griffiths singularities in equilibrium thermodynamics originate from slow modes, which are comes from coherent tunneling. And the Griffiths singularities in real-time dynamics originate from fast modes, because the regions are excited, and you can interpret them as being dynamically decoupled from the bulk. And I think that's the message I want to tell you. And thank you all for listening.
Thank you, Jose, for a super nice talk. It's time for questions. Do we have any questions from the audience?
Yeah, I'd like to ask something, Jose. People with the same or similar Hamiltonian study what they call many-body localization for isolated systems. Now, this is an isolated system that you studied, and so how does this relate to things like pre-thermalization, etc.? Is there a many-body localized phase in this phase diagram, and how does this dynamics? Where does it fit in the
Okay, I didn't want to go into many-body localization. You can ask what does it have to do with many-body localization if you can map to free fermions, and in this case you would not say it's many-body localized, because this is a free fermionic system. But we can break integrability by putting, I don't know, next neighbor interaction or some other sort of interaction that would break it. And my claim is that this picture here would still be correct. And why is that? When you do the quench, this rare region here is locally in the ferromagnetic side. Doesn't matter if I'm talking about an integral or non-integral model. And the excitations here are in character very different from the excitations of the bulk, which is in the paramagnetic side. So the excitations will not fall into the bulk, will not tunnel to the bulk right away, because some emergent quantum number here must be conserved in the ferromagnetic side, in the rare region. And therefore it has to tunnel many times until it decays. Another way to see that is that, remember that the bulk is gapped, so it doesn't accept any excitations right away. So
well,
this picture,
you said, first of all, the first question is, does this system that you study, does it thermalize? It seems to, at very long times, it will thermalize, right?
No, these will not thermalize, because this is the integrable one. But as I'm telling you, if I put...
Yeah, so okay, but if you put the nearest neighbor, say, or something, then it will
break
thermalize.
integrability, okay.
It will thermalize.
It will take a long time, so the excitations will go to the bulk, and they will, I would, hopefully they will thermalize. But people that believe on many-body localization, they will say they will not thermalize. So I cannot tell you what's the right answer.
Well, you know what's confusing? You said this is something that happens in short times, and that's plausible. You have very good evidence there. But how short compared to what? Because my understanding is in this pre-thermal phase, it will thermalize, but at exponentially long times. So in practical terms, it will never thermalize.
Yeah, I agree with you. I agree with that.
So where does this, what you're talking, fit in that picture? That's my question.
Sorry, can you repeat the question?
Where does the dynamics that you have discovered, how does it fit into this picture of
Yeah, the dynamics is these quasi-particles. These are the cone lights, because when you cross, when the rare region cross its quantum phase transition, it's in the ferromagnetic side. So it has many quasi-particles now, that because you did the quench, and these quasi-particles are up there in the sky, and they are fast. They will depend on the local J of the rare region. So it's a non-universal answer. Some rare regions are faster than the quasi-particle in some rare regions are faster than the other ones, but these are all of order of J of the local J. So that's why it's short-time physics. Short-time physics is on the parameters of the rare region, right? If the rare region does not, if the quench is such that the rare region barely cross its quantum phase transition, and that there are some rare regions that has this character, the quasi-particles are slow, because they are very near to the quantum critical point. So the short time here will be, I don't know, 10 order of 10 time 10 or something like that. But for this red one that I'm showing you here, already, I don't know, this is, I had the free energy for this one, and the peaks appears around 1 or 2.
So in short, there is no connection of this to MBL concepts, right? You cannot make any connection.
The connection I told you was that I just said, if you break integrability, things will start tunneling slowly, and but if they tunnel all the way through or not, this is an open question. That's my feeling of MBL field. It's still open. There are people claiming now that things will thermalize in a long time. People claims, some other claim not. So the answer to your question is that it's an open question. I don't know.
Okay.
Do we have any other questions from the audience?
I have a related question in terms of because you talked about the fact that they don't thermalize, or because they're localized and they're kind of decoupled, so there is probably not much room to go. Is there an analogy with quantum scars here? Like because it is true that they are integrables, but I'm just the fact that they're not thermalizing. Is there an analogy with the not many body scars, just like quantum scars, but still a free fermion chain?
The definition of a quantum scar is evading my mind now.
They basically they break ergodicity and ETH in some sense locally.
It's because the overlap of these state with the others. How is that? I don't.
It's a mixed phase space of sort, and then they basically just don't have almost closed orbits in phase space, so they kind of don't really have a truly chaotic trajectory, and therefore it's not the same description because it's which you are using here, but the fact that there's a genuine lack of thermalization even in an integrable system in these locally. That's why I was asking.
The honest answer is I don't know. I have to check. Yes, but yeah, I don't know. I don't know if there are quantum scars here. I don't think so, but I may be wrong.
Thanks. Oh, very interesting talk. Thanks.
Thank you.
Any other questions? All right. If not, let's thank Jose one more time. And thank you everyone for joining us. Bye, everyone.